Hello and welcome to the lectures on QED and QCD within the RAL Summer School. My name is Jeppe Rosenkrantz Andersen and I'm an Associate Professor at the Institute for Particle Physics Phenomenology at the University of Durham. My job here is to guide you through the course. There are lecture notes and you're welcome to send me questions by email or contact me in the discussion group sessions. Now you might ask, what is QED and QCD? Quantum electrodynamics started life as a study of the interactions between electrons and photons. It is, of course, now understood as a subgroup of the broken SU2 cross U1 of the Standard Model. And it describes the interactions of fermions with massless gauge bosons dictated by a symmetry group of U1. Now QCD is then the slightly more complicated interactions dictated by the gauge group SU3, but it is still interactions between fermions and massless gauge bosons. And that's why the study of the two gauge groups are often put together. The gauge bosons are massless. So, in order to describe the dynamics of particles involved in high-energy collisions, one needs to be able to describe the interactions at the smallest distances, smaller scales, quantum mechanics, and the effects of particles moving at very high energy, meaning relativity. So in order to derive the equations quantum mechanically that are necessary to describe these effects, let's see what happens first when we study the Hamiltonian of a non-relativistic. When we study the Hamiltonian for a particle in non-relativistic mechanics. So we have here that the energy of the particle is equal to its momentum squared divided by 2m plus the potential. Let's just make it one-dimensional. We could even make it three-dimensional. Now, to convert this into a wave equation for quantum wave mechanics, we use the standard identifiers of the energy becomes I times the time derivative of the wave equation or wave function, and the momentum is identified as minus I times the derivative with respect to x, y, and z. Now in all of this course I will of course use the natural units of h bar is equal to c is equal to 1. Now the plane wave solution phi tx will take the form of having an exponential minus I e times t minus p dot x, which we just write as e to minus I p dot x in 4-vector notation. So if we apply the differential equation of taking the derivative with respect to t, or rather the identification of the Hamiltonian applied to the wave function, we find that I d dt, I'll just write that as dt, phi t comma x, according to the equation up here, has to be equal to minus 1 over 2m times the square of the derivative plus the potential. We will call this function the energy, we'll call the Hamiltonian, which is of course identified as the operator which gives the time evolution. H here is called the Hamiltonian. This is the Schrödinger equation. The cornerstone of normal quantum mechanics. But of course, we can't expect this equation to be relativistically covariant because A, time only appears with one derivative and the spatial coordinates appear with double derivatives, and of course we know that a Lorentz transformation will mix the time and the spatial components of the equations, so they should really arise at the same order for the equation to have any chance of being relativistically covariant. But of course, we also know that we didn't start from a relativistically covariant equation. We started from the normal half mv squared expression for the energy, so there's no chance that whatever we did to that equation will suddenly become relativistically covariant. So in order to derive a similar equation that has at least the property of being relatively covariant, let's start from the identification in relativity that E squared is mc squared or m squared plus p squared. Now, again, we can convert this to a operator equation for the wave function by identifying p mu as I d mu in 4-vector notation. Like we had before, the energy was identified with I dt and the momentum by minus I, the spatial derivative. We just write that in 4-vector notation here. P mu is I d mu. And then the corresponding wave equation for a arbitrary scalar wave function phi would be written as dt squared minus Nabla squared plus m squared phi t comma x, which in 4-vector notation we would write as d mu plus m squared on phi, and then just write x in 4-vector notation. And of course this can also be written as the D'Alembertian, which is just the d mu plus m squared phi on x is equal to 0. Good. This is the Klein-Gordon equation. And it's a relativistically covariant quantum mechanical wave equation for the motion of a free scalar field. Now, of course, we can explicitly check that it is Lorentz invariant, but that rests just on d mu being Lorentz covariant. Now, I'm sure you've seen that in your undergraduate degrees, otherwise you can have a look in the lecture notes. So, we've derived here the Klein-Gordon wave equation for quantum mechanics, which describes the dynamics of fields, scalar fields. So particles with no spin. Now, the Klein-Gordon wave equation, of course, since it starts from a Lorentz invariant equation with E squared, will have both negative and positive energy solutions, because in order to find the solution for E, one will have to take a square root, plus or minus. Now that was so troubling to Dirac that he sought to find a wave equation which only permitted positive energy solutions. Of course, in order to avoid the square root here, one will need a linear equation in E. If it has to be linear in E and be relativistically covariant, then it needs also to be only linear in the space derivatives. We'll see later that Dirac didn't actually solve the problem of negative energy solutions. One had to come up with an interpretation of them. But before we get to that, let's just investigate here the transformation properties of the Clanborn equation. We want to see that it is indeed relativistically invariant. Now, under Lorentz transformation, of course, we have that x mu goes into x prime mu, which is, if we let lambda be the rank 2 tensor describing the Lorentz transformation, will be lambda mu nu x nu, which means that the derivative will translate into d prime mu. So if x mu translates as a contravariant 4 vector, the derivative of a covariant 4 vector will then translate as d prime mu, which is lambda inverse rho mu d rho. Now, the field phi is a scalar here, and what that means is that under Lorentz transformation, phi of x translates into phi prime of x prime, which is phi prime. We know what x prime is, that's just lambda operating on x. I left out the index notation there, which is equal to, since it's a scalar, phi of x. That's the definition of a scalar field. Now, therefore, the Clanborn equation in the prime system will read that d prime mu plus m squared, all acting on phi prime on x prime of x prime, is equal to, we know how the derivatives translate, so that will be lambda inverse rho mu d rho, then there will be a lambda inverse sigma nu d sigma g mu nu, to contract them, plus m squared, all acting on phi prime lambda x. But since I've used here index notation, everything commutes. So if we pull the derivatives to the front, then we've got here d rho d sigma, and then lambda inverse rho mu and lambda inverse sigma nu, we think of them acting on the metric g mu nu. But of course the metric is the same in all frames, so what we get is just g rho sigma plus m squared is invariant. Now phi prime on lambda x is just phi of x, since phi is a scalar. Now, so if we start with a scalar field that satisfies the Klein-Gordon equation in one frame, the unprime frame, then this is zero. and therefore it also satisfies the Klein-Gordon equation in the prime frame. So indeed, the Klein-Gordon equation is relativistically invariant. That's good. As I said, the Klein-Gordon wave equation will have both positive and negative energy solutions. And that was so troubling to Dirac that he set out on a quest to find a relativistically invariant wave equation that only permitted positive energy solutions. Now, of course, if it has to permit only positive energy solutions, then it can be only linear, not quadratic, in E. You have to avoid the plus minus square root solutions. If it has to be linear in E, it must also be linear in the derivatives, space-time derivatives, in order to be relativistically covariant. We'll see later that actually Dirac's efforts didn't solve the problem with the negative energy solution, but what he did find was a very important wave equation for fields with internal spin, for spin-half particles, fermions. Let us see how he went about doing that. So, the Dirac equation. So we're seeking an equation which satisfies E squared equals m squared plus p squared, but the wave equation itself should only be linear in the time derivatives. C, wave equation. Linear in dt in the time derivative, and solves, and where the solutions to the wave equations also solve E squared is equal to m squared plus p squared from relativity. Now, since it must be linear in dt, let's say that I dt on our field psi t and x must be equal to something that is linear in the spatial derivative. Let's write that as minus I and then some vector alpha dotted with the spatial derivatives plus beta m psi t comma x. So what we want is that this solution essentially also is a solution to the Klein-Gordon wave equation in order to satisfy E squared equals m squared plus p squared. Because the solution to the Klein-Gordon wave equation will automatically fulfill E squared equals m squared plus p squared. So essentially what Dirac wanted to do was to find a linear equation that automatically took the square root of the Klein-Gordon wave equation. Now, to see what constraints this puts on alpha and beta, let's square this equation here. So square the star, plug it into the Klein-Gordon wave equation, we find that minus the t squared psi on t x is equal to I dt, we just did that and once. So I dt, so minus dt squared is I dt times I dt. Now 1 I dt on psi, we know if it solves the Dirac equation, is minus I alpha delta, sorry, nabla plus beta m. So this here is minus I alpha nabla plus beta m psi t and x. Now the second I dt we also replace by the Dirac equation as minus I alpha dot nabla plus beta m. So this is equal to minus I alpha dot nabla plus beta m squared on psi t and x. And now we simply just write out, using index notation, what this bracket here is. That is, of course, if we write it out in index notation, it's minus the square in the first term, it's alpha I, alpha j, di, dj, j equals 1, 2, 3, minus I, beta alpha I, plus alpha I, beta m di, that's the cross term, and then there's a plus beta squared m squared on psi t and x. Now we require that this solves the Clanborn equation. We require that whatever solves psi also solves the Clanborn wave equation. Now, the Clanborn wave equation requires that the right hand side is equal to minus nabla squared plus m squared gx. So what we require is that this differential operator here is nothing but minus nabla squared plus m squared. Therefore, the vector alpha and the number beta must satisfy that alpha I alpha j plus alpha j alpha I, which is the anti-commutator alpha I comma alpha j, must only give us a number, a non-zero, when ij is equal to each other, and in that case it should give us 2. And also the condition is that beta alpha I plus alpha I beta, which is the anti-commutator alpha I comma beta, must be equal to 0, right? The Clanborn equation has nothing of the middle terms here. Beta alpha plus alpha beta is 0. In the Clanborn equation, there's no linear term in the mass. And also, we must have that beta squared is equal to 1. Just the last term here, just give us n squared. With that, the solutions to the Dirac equation would also solve the Clanborn equation. Now, if alpha I and beta are just numbers, these equations cannot be solved. We cannot find solutions to this algebra that is written up here, the three conditions on alpha I and beta. However, for n by n matrices, one can indeed find solutions to this algebra, the Dirac algebra. Now, if alpha and beta are matrices, of course, psi is no longer just a number, but must be a column vector. So to find solutions for alpha I and beta, one needs n by n matrices. Numbers doesn't do it alone. So psi is then a n column vector. Even then, the solutions aren't immediate. So the conditions here will transpire to be the conditions of the matrices that trace on alpha I, 0, and so the trace on beta. So there must be traceless matrices. One can also see that it will be that the eigenvalues of these matrices will be plus minus 1. Now, this means that n must be even the dimension of the matrices. That's quite easy to show, actually. I'll leave that as an exercise, but it is really easy to show. Now, in 2 dimensions, it will turn out that there's still not enough linearly independent matrices to satisfy these conditions, at least for non-zero masses. But there are solutions in 4 dimensions. Four here, meaning n equals 4, not space-time dimensions. So one such solution is that alpha I is equal to 0, sigma I 0, and beta is the identity matrix, 2-dimensional, 0, 0, minus 1. Where sigma is a vector of the Pauli matrices two by two, and 1 is the 2 by 2 identity matrix. So we've now formed an equation which may be thought of as the square root of the Clanborn equation. We just need to check that it's Lorentz covariant. To show that, we first define the new matrices, gamma naught is equal to beta, and the spatial components of gamma are equal to beta times alpha. Then we form a 4-vector, we call it gamma mu, which is gamma 0, comma gamma, a vector of matrices, where mu is a Lorentz index. Now, each component of gamma mu is itself a 4x4 matrix. In terms of the gamma matrices, one can now write the conditions for beta and alpha. That we have here, those three conditions. One can write them as the anti-commutator of gamma mu with gamma nu, which is gamma mu plus gamma nu, that's the definition of the anti-commutator, is equal to 2 g mu nu. Now, this is an example of what's called a Clifford algebra, and any set of matrices that satisfy this condition can be used to construct the Dirac equation. The representation we saw before, using the Pauli matrices, is just one such example of a Clifford algebra. And that's known as the Dirac representation. But any other set of matrices satisfying alpha, new set of matrices, alpha prime I equals a unitary matrix, alpha u minus 1, and beta prime equals u, beta u minus 1, u unitary, will also be suitable, will also satisfy the Clifford algebra. Now, if we multiply by gamma 0, then one can write the Dirac equation in a covariant form as I gamma mu d mu minus m, and then the 4x4 unity matrix in spinor space psi t comma x, which in Dirac notation becomes I d slash minus m. We drop the 4x4 notation for the spin indices, they are understood, psi x is equal to 0, where a slash is a mu, gamma mu, a mu. Now, the equation here is called the Dirac equation. And here it's expressed in position space. If we express it in momentum space, that is replacing d mu with I p mu, then the Dirac equation becomes gamma mu p mu minus m, let's include the 4 psi p is equal to 0. Where psi is here is a column vector. Meaning it has 4 entries here. It's not a scalar. Now, this means that it contains more than 1 degree of freedom, obviously, it contains 4. And Dirac exploited this property to interpret his equation as the wave equation for spin half particles, fermions, which can be either spin up or spin down. And the column vector psi is known as the Dirac spinor. And the 4x4 matrices act in spinor space. The matrices, gamma mu, operate on these Dirac spinors. Thank you.